speaker is Tyrus Berry from George Mason University. And yeah, so please go ahead, Tyrus.
Thank you. So I want to start by acknowledging my collaborators, John Harlem and Dimitris Giannakis, and also NSF for supporting some of this research. So I want to talk about optimal bases for data-driven. So we're doing forecasting here, but data-driven forecasting. And I want to start by motivating why we want to be estimating a forecast operator by just looking at some basic perspectives from trying to forecast with data. So if we start at the very beginning, so I would talk about deterministic UQ and then stochastic to kind of build my way up. So if we start at the very beginning, just deterministic forecasting, we just have a nice deterministic model here. Stick with discrete time for simplicity. And so essentially, if you're trying to learn this kind of dynamics from data, it's essentially kind of a regression problem. Your goal is to learn the function f. But already there's sort of two choices. You can do what I would call iterative methods, where you try to actually just approximate the one-time step forecast function. And then if you want to forecast further into the future, you just iterate that by applying the one-step forecast multiple times. Or you can do what I would call direct methods, where you can actually build a different interpolator for each forecast time. So an interpolator for the time 1 forecast, an interpolator for the time 2 forecast. And these have sort of different behaviors typically. So here I'm showing a direct forecast. This is just a local linear forecast for a Lorentz system. But this is sort of just characteristic behavior of what you would expect to see. So on the x-axis is the forecast horizon, how far into the future you're forecasting. And on the y-axis is the mean squared error. And so here, this dotted line is just the mean squared error of just predicting the average, right? So you could always have a really dumb predictor that just always predicts the average of the dynamics, and that would just produce an error that was the size of the standard deviation of the dynamics. And so if you do this direct forecast, what you tend to see is the forecast scale sort of decays a little bit more rapidly, but it does sort of capture the true invariant measure a little bit better. Like it sort of, in the long-term forecast, because you're approximating this function that's sending stuff all over the place, you're going to get, you're basically going to get the mean in the long-term forecast. Whereas an iterative forecast tends to produce trajectories that look a lot like the trajectories of the dynamics. And it tends to do much better in the short-term forecast, but eventually it decouples from the truth. And now you have sort of the truth and the forecast going around the attractor. And that's sort of a worse prediction than just predicting the mean, right? So in the long-term forecast, it sort of has this bias effect where it's actually worse than predicting the mean in the long term. And so the probabilistic approach kind of cuts between these two, right? Where instead of trying to predict a single trajectory or just predict the expected value of the trajectory, you kind of, you build an ensemble, let's say, right? An ensemble around the initial condition, and you let that go. And so that manages to track the forecast for an amount of time, but when it spreads out, the different ensemble members are all in different parts of the attractor, and so their average is still looking like the average of the attractor. So that's sort of, so that's already a bit, a difference just in deterministic forecasting between iterative and direct, and sort of motivates why you might want to do a probabilistic forecast, even if you don't have a UQ problem. So within the realm of deterministic forecasting, we're going to sort of come back to this later. So I wanted to just sort of do a comparison of the different interpolation methods that are out there. This is not exhaustive, but there's sort of a lot of similarities between them. So way back in the 80s, people were already playing around with local linear regressions to try to approximate dynamics from data. So the idea here is you've got some new point X that you want to do a forecast on. What do? You find the near neighbors of X in data space, okay? And so this xj might be the nearest neighbor, or it might be the mean of the nearest neighbors of X. And then you just do a local linear approximation here, assuming that F is somehow smooth. So that's one method. And so this DF implicitly is just fit using sort of backslash, sort of doing a least squares regression to find the best linear fit between, your neighbors and where they went from the historical data. So the type of method that I'm working with are based on what are called kernel regressions. They're sort of an outgrowth of kernel regression methods. And here what you do is you try to take your function f and approximate it as a linear combination of some basis functions. Okay, so that's going to be one of the questions in this talk is what are the right basis functions to use? And in the world of kernel regression, the typical type of basis functions that you use are bump functions. Okay, so already there's this nice similarity to what was happening in the local linear regression. So h here is a function that sort of decays, and you plug in a distance, and so as the distances get really large, the h function decays, and so essentially the point x is only interacting with nearby points, and the decay of h sort of controls, you know, how close, how localized this function is. Now, on the other side, and this is the sort of methods that I'm trying to, you know, understand a little bit better how they relate, but there is sort of a similarity here. So if you go into neural networks, you'll see a lot of functions that look like this. Okay, so now what happens is instead of h being a bump function, h is a sigmoid function, and so they write h, and so instead of having the function h depend explicitly on the historical data, so xj here would be historical data, in neural networks, they introduce parameters, right? So the x comes in and it gets, you know, hit with some parameter aj, and then it has a shift. So you just have an affine transformation here before going into the sigmoid. And the way they explain this is that they're sort of adjusting the, you know, they're adjusting the sigmoid, right? So that it's sort of centered around the active area of the data. But there's sort of another way to think about this, is if you take this constant bj, you could always write that as aj transpose times some xj. Okay, now xj is not actually a data point, so I want to think of it as sort of a pseudo data point. So I just want to make their formalism look a little bit more like mine. So if you do that, I guess I should put a minus sign here as well. If you do that and factor out the aj, then you can still think of this as some nonlinear transformation of the difference between x and a data point. It's just this data point is no longer one of your training data points. It's now sort of an artificial data point that they've learned using, so they fit these parameters using some kind of nonlinear regression. And so you can still think of it sort of in this context where there's these sort of implicit data points. And that may be one advantage of the neural networks, is that they're not constrained to using, see, we're sort of constrained to using the data points from the historical data as our landmarks, whereas they're sort of allowed to pick their own landmarks. So that might be one interesting thing. Now, you know, building on these, I mean, this is sort of just the very, very genesis of neural networks, and then building on these to oversimplify, you have deep networks where you do compositions of these kind of approximations, and then reservoir computers, which are actually even more closely connected to kernel regression, because in the reservoir computers, they sort of fix the AJs and the BJs and only estimate the CJs, which turns it into a linear regression problem rather than a nonlinear regression problem, and actually makes it a lot more similar to the kernel regression. So there's several differences, you know, that are interesting to explore here that I just wanted to elucidate for people who are interested in these kind of problems, which are, you know, kernel regression sort of works with bump functions versus all these neural network methods working with sigmoid functions. And bump functions are a lot easier to analyze theoretically, because we sort of have lots of, you know, results about approximating things in terms of bump functions. Sigmoids are a little bit trickier to analyze theoretically, and there's other reasons as well. But I will say there's been a huge amount of success in applying these kind of methods. And so I think it's something that just, you know, if we could explore these connections more thoroughly, it would be really interesting. That's sort of why I wanted to bring this up so early in the talk. So getting back to forecasting here. So again, remember we had this, you know, this deterministic forecasting problem is essentially sort of a regression problem. And if you're doing uncertainty quantification for a deterministic problem, you can still kind of play it like a regression problem if you want to, right? So now the idea is you have some probability distribution at time k. You want to push that forward and figure out what the distribution is at time k plus 1. Well, if the dynamics are purely deterministic, you just need to take that, you know, the current probability distribution and sort of advect it forward along the trajectory of the dynamics. So if I can regress, if I can fit this function f from data, then I could just combine with an ensemble forecast to try to do some uncertainty quantification. So that's one option. But there is another option, right, which has become a lot, you know, sort of really opened up, you know, the research area here, which is that you can try to instead think of this push forward as an operator. So I can think of f star as an operator that's mapping probability distributions to probability distributions. And I can reformulate the question. Instead of trying to regress and learn this function f, I can say, well, instead I'm trying to learn an operator L. And that perspective sort of changes how you might think of this problem. And so, you know, if I'm trying to represent an operator, the natural thing to do is sort of pick a nice basis and then come up with a matrix representation of my operator, if I can find a nice orthonormal basis, right? And so you could, you know, if you sort of know what your dynamics are, you might have some, you know, good insights into how to pick the basis, but we're not in that situation. We're sort of in a, we're in the data-driven you know, we're trying to learn the dynamics from the data. And so the question becomes, what's going to be a good basis? And I should, let's see. So I just want to sort of preview here a little bit, right? Once you choose a basis, right, you can kind of get the representation of this forecast operator pretty easily here, just by sort of averaging the basis elements on the current time against the basis elements at the one-step forecast. Because when I take one of the basis elements and I pre-compose it with f, all that's doing is pushing it forward in time. So this will come back in just a few slides. So this leads us to stochastic forecasting, and now we can no longer really think of it as a regression problem at all, right? So now there's the function that we're trying to learn is not a deterministic function. It depends on some stochastic perturbation omega, and you know, often this will enter linearly, but you know, for more generality, we can think of it entering non-linearly. And we don't just want the mean dynamics, right? So we don't want to just average out the stochastic component, because what we want to do is when we push forward a distribution in time, what we have to do is we have to compose it with the stochastic term and then integrate out the possibilities for the stochastic perturbation. And that's not the same as first integrating out the stochastics and then composing. Okay, so we really do need to think of this L operator now and try to approximate that. So we no longer can have the choice of thinking of this as a regression problem. So I just want to say that, you know, while there are these powerful regression methods, I think those need to be sort of adapted. Like things like neural networks, you know, there must be ways, or I'm hoping that there's ways to sort of maintain the power of those methods, but somehow adapt them into full stochastic forecasting methods, you know, rather than just doing a regression and then trying to use an ensemble forecast. I mean, that's one possibility, but I think when you talk about stochastic forecasting, it really becomes an operator estimation problem. So that's the first thing I wanted to motivate here, is why data-driven forecasting should be thought of as an operator estimation problem. The second question, the second part of the talk is, what's the right basis, right? So once you sort of accept that it's an operator estimation problem, then your goal should be to find a nice representation of your operator in a nice basis. And so what are the possible choices, or what's the right choice? And so here we want to consider the possible error sources. So we're going to be estimating this using some kind of Monte Carlo summation. So immediately we're going to have a variance. We could potentially also have a bias here, right, where the expected value of this over the data set is not actually equal to the true forecast. And then finally, we've got a more complicated error, which is the truncation error, which comes from the fact that we're taking this infinite dimensional operator and just truncating it on this finite, you know, ultimately we're going to have to truncate this matrix and not have the full matrix representation. And then there could be continuous parts of the spectrum that we're losing as well. So truncation becomes a significant issue. So you know, how should we go about thinking about what's the right basis? And so I want to argue that for certain classes of L, a good basis will leverage smoothness in order to try to minimize the variance. And so that's what's going to come. That's sort of what I want to talk about next. But we also want our basis to capture the global structure, right? We don't want a bunch of basis functions that are all just in one part of the attractor. They need to be spread out over the whole attractor to capture the global behavior. Okay, so when it comes to choosing a basis, the method that I focus on is coming from manifold learning, and it's really motivated by this idea of let's choose a smooth basis that captures the global structure. And so I think of manifold learning as, you know, you have this data set and it's living on a subset of data space, which is a nice manifold. So, you know, you could imagine also, like in the PDE world, if you have a PDE that collapses onto or near an inertial manifold or something like that, there could be lower dimensional structure in the data set, and you want to try to leverage that. So the way that manifold learning tries to take advantage of that is it doesn't try to learn the actual point set of the manifold. Instead, what it does is it tries to learn a nice basis for functions on the manifold, and it does that by estimating a Laplace operator. So the idea is that on a general manifold, you can define a Laplace Beltrami operator, and at least on a compact manifold, it will have a nice set of eigenfunctions, and those will form an orthonormal basis for square integrable functions on the manifold. But they're not just any nice basis. So this basis also minimizes this smoothness functional or this roughness functional. So if you think of integrating the gradient of a function, that sort of measures, that's the classic Dirichlet energy. It sort of measures how oscillatory the function is. And so these basis functions are trying to be as smooth as possible. They're trying to minimize this measure of oscillation.
Sorry, Tyrus.
Sure.
So we're into the time that's for the question period. So we've got a few minutes left, and that's okay to use up this time. But then and then we take the questions offline. But,
okay. Well, let me just jump sort of ahead then a little bit. So the point is, you can estimate these nice smooth functions from data, and what's the motivation for that? The motivation is that these functions actually minimize the error. So here's the A's that you're trying to estimate. These are the representation of the forecast operator and the basis, and these are your data-driven estimations. And so what you can show is that that they're unbiased estimators, but they have an error that depends on the gradient of the basis functions that you chose. And so then it's sort of a natural choice to minimize the gradient of the basis functions. So that's sort of one way to go about choosing your basis, is you want to try to minimize the gradient, and you can do that by choosing eigenfunctions of an appropriate Laplace operator. And so that's one way to motivate choosing a basis. So let's see, so I had a lot more to talk about potentially, but I just want to say that real briefly, because it leads into the next talk, is that this method of forecasting that I'm talking about, it runs into significant problems because of the cursive dimensionality, right? And so if you have this data set and you're trying to reconstruct this attractor, and the attractor is 13-dimensional, right? You're not going to be able to reconstruct the attractor and learn it from data. And so one potential step forward is through this Morisot-Sig formalism, which tries to decompose dynamics. So instead of thinking of it as a fully reconstructed dynamics, you think of it as trying to approximate a projection of dynamics, okay, which is going to be a stochastic system. And in that case, there's this sort of decomposition into a Markovian, a memory, and a stochastic term, and all we're capturing at the moment is the Markovian and the stochastic term. And so I think there might be a way forward here as well by capturing also the missing memory term. And so that's what we're working on now, and I'm looking forward to learning more about Morisot-Sig from the next speaker. So sorry that was a bit quick, but if people
oh, okay. No, yeah, sorry, I'm sorry to interrupt.
No,
thank you, Tyrus. That's a very, very interesting talk. I wish we had more time to get to all of our speakers, because I would like to hear more about all the talks, but this is what we have. So by my watch, I think we have time for one very quick question. So Helen has a question.
Wait, Kevin. Wait a second. I think Tyrus has until 11 to move to next speaker. So he has.
Oh, did I screw up the time? Oh, I'm sorry.
I thought that seemed quick.
Yeah, no, I'm sorry. I wrote down when the talk should end, and okay, my mistake. I apologize. You ended actually just a little bit before the allotted speaking time.
Okay.
I'm sorry. Yeah, my bad. So Helen has a question. Yeah. Okay, so I'll just read it. So about the Helen's question is about minimizing the gradient of basis function. Is that okay? So the question is regarding the minimization of gradient of basis function. Is it because of the Laplacian operator?
Yes. So the Laplacian operator is connected basically, so basically, like if you take the inner product of both sides of this with phi j, and then you realize that the Laplacian is div grad, and you move the div, over to the other side, you get grad phi, grad phi dot grad phi. And so the Laplacian is intimately connected with this Dirichlet energy. And so that's why the Laplacian is sort of the right operator if what you need to minimize is the integral of the gradient. And so it just so happens that if you're trying to forecast sort of a classic stochastic system, right, then this is sort of what I skipped, is that this shift operator, when you take a function and you try to look at its expected value in future time, that's given by this forecast, the forecast operator, the Kolmogorov operator applied to the function. But when you evaluate that on a particular data set, that's the expected value. But when you look at the actual value, it's equal to its expected value plus some error terms. Okay, and so you can derive what those error terms are. This one has mean 0 and its variance is on order tau, the time step. And so the dominant error term here is this guy. And so basically the dominant error that you get, sort of the stochastic error that arises from trying to learn this operator from data, has to do with how smooth the function is, okay? And it's order square root of tau, where tau is the time step. And so that's why the gradient of the function sort of naturally arises. And so when you go to try to forecast by projecting down into some basis, you want to choose a basis that minimizes this error. Now, that there's other sources of error here that we haven't mentioned, right? Which is that we're also taking this infinite dimensional dynamical system and projecting it down onto a finite basis, and so we have truncation error as well. So there may be some interplay between you're getting sort of the best possible estimates for the coefficients, but are you getting the best truncation error as well? That's a question we haven't answered yet.
May I ask a question? So Tyrus, in the one-step prediction, I can see that you have a Markov process from SDE. You use the Laplacian-Beltrami operator is perfect. And then I think at the beginning you mentioned that you have multi-step prediction. In that way, you will have multi-step as the function to be regression. And f will be dependent on multi-steps. In that case, as you mentioned about the Morris-Vanzig part, that will be a delayed part. Then in that case, can you still use this Laplacian-Beltrami operator? Because it's no longer a Markov process.
So again, so we don't actually use the Laplace-Beltrami to do the forecast. We use the Laplace-Beltrami to get the basis. And then once we get the basis, then we build, but you're right. So once we get the basis, right, then we take the true operator, which is sort of given by the one-step map on the data, and we represent that operator in the basis. But this is a purely Markovian representation. And so we are missing out on the memory terms. Now, what you can do to gain some of the memory terms back is you can try to add delays. So you can do this time delay embedding trick, right? So that's one way to try to get information from the past into the Markovian representation. But the problem with that is, as you add more delays, essentially what you're trying to do is you're trying to reconstruct the whole attractor, which is not possible. And so then you won't be able to get your basis functions anymore. So this is a sort of competing thing here. So that I have a sort of picture here where you can play this game. So like the dark blue here in the background is what happens if you don't do any delays. So this is using a projection of a Lorentz 96 system, a one-dimensional projection. And you're trying to predict this into the future. And so if you add one delay, the forecast gets a little bit better. If you add 4 delays, the forecast gets a little bit better. But if you add 9 delays, it gets worse, right? And it just gets worse and worse from there. So you can never reconstruct the whole system because it's too high dimensional. It's like a 13-dimensional attractor. And so the question then becomes, can I do a partial reconstruction? Can I do 4 delays? And then instead of trying to build this Markovian system, which is what the diffusion forecast does, can I somehow augment that to have a non-Markovian term? And that's what I haven't quite figured out how to do that yet, but I'm motivated to learn about Morris-Vanzig to try to understand that.
Thank you.
Thank you, Tyrus. So there's one more question from Felix in the Q&A, but I'm not sure we have time for it now. So maybe I can ask you to address that